Okay, now I request Parmeshwaran Nair to chair this session and then conduct the program.
Thank you, TRG. So I'm supposed to be the chair, crack my whip when it's 40 minutes, and stop you all from talking. But let me first start by congratulating Bal. And there will be many talks showcasing the many facets of his work during the next 5 days or 6 days. So let's start the session without further ado. The first speaker is Denjoe from Dublin Institute for Advanced Study, and he's going to tell us about multimatrix invariants.
Thank you very much for the opportunity to speak, and thanks to the organizers for putting such a nice program together and such a warm welcome. And congratulations to Bal for his on his 85th. When one meets him, one is always surprised that he is not in his 30s or something like that. I got to know Bal originally when I was a postdoc in Syracuse in 1987, and his 316 lectures drew everyone in, and I got captured as part of that. I was part of the gravity group, but still was broadly in Bal's orbit, let's put it that way. And we collaborated more when I took up a permanent position in Mexico later, and I found that he had close connections which predate me by many years to the Dublin Institute for Advanced Studies, where I think he was almost recruited at one point. But that's another story. So I'm not going to take more time. There's probably a second microphone on there. I want to tell you about counting multimatrix invariants. Bal has heard this lecture already, more or less, but hopefully I have answered some of the questions that he asked at the last time he heard it in this one. Let's see. So, okay, good. You've seen the abstract already. So, I want to tell you, first of all, the context in where these multi-matrix models emerge and part of the interest in them. And I just thought the simplest place to tell you where they emerge is just to consider Yang-Mills in 4 dimensions, 5 dimensions, whatever dimension you want, but I've taken 4 dimensions. And if I compactify it on T3, the tree torus, and I just take the constant modes in that compactification, I get a dimensional reduction of the model, of dimensional reduction of Yang-Mills to 0 plus 1, where time is the only variable left. I get a multi-matrix model, which I've written here below. And it is, the coupling constant is going to be rescaled, of course. So I pulled out the volume of the tree torus from that. And we get this double commutator, which, since only the commutator survive, and we've matrices I is equal to 1 up to D, 3, or in the case of standard Yang-Mills, but there's still a covariant derivative left. These are the multi-matrix models. This type of multi-matrix model is what is of interest here. One could dimensionally reduce it to 0 dimensions and get standard multi-matrix models. These variety here would be called multi-matrix quantum mechanics, whereas if I reduced it to 0 dimensions, got rid of time as well, you would have multi-matrix models. And what I'm interested in is counting the invariants of such models. The same action as a curiosity arises if you use Lightcone gauge fixing and Hoppe-Goldstone quantization of a membrane propagating in 3 plus 1 dimensions. And that's also of interest. If I didn't do the Hoppe-Goldstone quantization, the dt would be a covariant derivative with volume-preserving diffeomorphisms. That's just an aside. It's stuck again. This is not going to work very well. Something. Sorry? Well, it wasn't necessary to point it earlier, but it's just losing. The computer is not responding to it either, you see, so. It's freezing. So the invariants, I'm interested in counting the invariants associated with this. So what are the invariants? The invariants are what's left when you do, when you change coordinates for the matrices. In other words, when you do a GLN transformation on the left or right and a joint transformation for a square matrix. You can consider an n by n matrix, and if I consider, I'm just calling X to be a generic n by n matrix. It has n squared degrees of freedom, and there are just n invariants, and of course they are the eigenvalues of the matrix. The eigenvalues are the roots of the characteristic polynomial, Pn, which is the determinant of x minus lambda times the identity. And we know from the Cayley-Hamilton theorem that every finite rank square matrix satisfies its own characteristic polynomial. Pn of x is equal to 0, where Pn is the characteristic polynomial. Pn of lambda would be the characteristic polynomial given by this determinant. If there's a well-known, or should be well-known, relation for generating the characteristic polynomial. It's due originally to Laverniere in 1854, and you can get Pn from Pn minus 1 via this expression here. You see that P1 is a 1 by 1 matrix, so P1 of x is equal to x minus trace of x. That's obviously true. It's going to be 0 if I put in x into this expression. Pn is generated by this iterative relation, and it tells you, since the x satisfies its own characteristic polynomial, Pn of x is equal to 0, and the trace must also be equal to 0. If I just use the trace being equal to 0, it tells me that I can express the determinant in terms of the traces. But if I multiply Pn of x by x, it tells me that trace of x to the n plus 1 can be re-expressed in terms of lower powers. So that's a trace relation. And just to see the content of it, I've just written it out for 2 by 2 matrices. P2 of x is given by this expression, x squared minus the x trace of x, etc. And it tells, we can see that trace of x cubed for any 2 by 2 matrix can be re-expressed in terms of the trace of x and the trace cubed of x and the trace of x squared. For 3 by 3 matrices, I just removed the trace to just show you what it is, and you get this rather simple expression: the trace of x of y to the 4th, y is traceless, is half of the trace of the matrix squared, and etc. These are just trivial things that are very classical. More generally, for an n by n matrix, as I said, you have the trace of n plus 1 is expressible in terms of the traces of lower dimensional ones. And the invariants, the set of n invariants are the traces of x to the power of k, from k being 1 up to n. And these are, of course, completely equivalent to the eigenvalues of the system. The invariants of the matrix, it's useful, if I'm going to count how many invariants there are, to just put the expressions into a generating function and write down the Zn of t as being the objects that are of interest, this dem n of n, which is what I'm trying to count, and put a variable with it, make a formal polynomial, sum it, and the sum from n equals 0 to infinity of dem n of n t to the n gives me this Zn of t. And if I've just got one matrix, then it's relatively easy to see that I know I have n variables that I'm going to write down. I've trace of x to the k, and I'm forming words in those ones, and the dim n must be given then in terms of the number of partitions of the integer n into capital N or less pieces. And you can then write down that the sum of this is just Zn of t, and you've got a generating function for your expression, and I've written out what it is, and this is it's standard to draw the partitions in terms of Ferrer diagrams. Okay. If I'm dealing with a matrices of creation annihilation operators, you can map the entire system into a Fock space, and we've got again trace of the matrix. Trace of the matrix, trace of the matrix squared, etc. And I've written out the those invariants and how they map in that setting. And again, we can get this partition function by the creation annihilation operators form a basis, and the number operator tells us how many of them there are. So we can form that Zn of t as being trace of e to the minus beta times this number operator. And again, you can write down that for a matrix, the product from 1 to n of 1 over 1 minus t to the m is this expression. One can derive that in a rather elementary fashion a little bit later. This is given, if n goes to infinity, then it's often frequently one would like to talk about the large n limit of such systems, and to discuss what's going on in the counting in large n. And z infinity is given by 1 over the Euler function, the Euler torsion. But the real question, as I introduced it, is what happens for multi-matrices. The eigenvalues are no longer that useful. They're going to be the invariants of one of them. I could diagonalize one of the matrices, and I've got n of the invariants, but I have many more matrices. For instance, I have x and y. I can diagonalize x, but not y. So what are the remaining invariants that one, and how should I describe them? And how many of them are there? What can one say about them? So one way of doing this, obviously such a question has emerged in the classical literature, and it seems to have emerged in around 1943, I think it is. I can't read it's in my, yeah, it doesn't matter. But was rediscovered later, and it is, one of the results is formulated in terms of what's called the Nagata-Higman theorem. And the Nagata-Higman theorem, I've written it out above it. It tells us that there is an important number, calligraphic n of n, which, and this is for nilpotent algebras, that n of n, which characterizes that system, and was used in the context of multi-matrices in this theorem of these guys here, and the book of processi is one of the more useful ones in this regard, and it tells us that there's a longest trace that we need to consider. And it also tells us that the invariants are the traces of matrices, of strings of matrices, and that there is a longest one, and the longest one is given by n of n. And what's known as well is that n of n is greater than n times n plus 1 over 2 and less than n squared. So that's the longest string of invariants, but it still doesn't tell us how many invariants there are. And I recommend this article of Drensky for a review of many of these things. The partition function that counts the number of invariants was related to the Hilbert it's called the Hilbert Quantary series in the maths literature, and it can be given by this Mullian-Boyle formula, which I've written out here, which is just a contour integral. And one can evaluate these ones, and Ti are formal variables for each of the matrices the one's considering. It looks relatively straightforward. The complication is that there are lots of poles. It becomes cumbersome to evaluate for more than 2 matrices, and even for even for 2 matrices, it has only been evaluated up to n is equal to 6 in terms of 2 variables and n equals 7 for 1 variable, and that was relatively recent. And the context in this setting was counting the BPS, the quarter BPS states of n equals 4 supersymmetric Yang-Mills. That was where they were interested in it. But one can do that integral for relatively small systems, and I've written out what it looks like for 2x2 matrices, and for 2 matrices, and the information that you can see in it is that it is 1 over 1 minus T1. T1 is telling us that one of the variables is the trace of the first matrix. We have T2, the trace of the second matrix, T1 squared, the trace of the first matrix squared, T2 squared, the trace of the second matrix squared, and T1, T2, which is the trace of the product of the matrices. And there are no further relations between them. It is freely generated by those ones. And you can see that the invariants are trace of x squared, we have these 5 invariants. If I take 3 matrices, we get something slightly more complicated, and there's a term on top, which is T1, T2, T3. The T1, T2, T3 does not appear as a square, so it is an elementary generator, and it corresponds to the trace of x, y, z, and it matches the longest chain that we would expect, longest string, with being 3, and trace of but its square satisfies a relation, so it's really just a Z2 variable that's in here. And what it is if you think of 2x2 matrices, you can think of 3 2x2 matrices. They form a tetrahedron, and the volume of the tetrahedron has an orientation, and that's that Z2 that's being picked up here. Go back to the quantum setting, and for Balachandran, one should always be quantum. That harmonic oscillator system that I described is given by this gauge Gaussian model, and I've taken the constant there to be 1, just for simplicity, and the covariant derivative, and I've written it as a trace, because we want to now just look at that trace of e to the minus beta times this creation annihilation operator, number operator. This action, the simplest way to derive the Mullian-Boyle formula is to treat this as a lattice gauge problem and do Euclidean path integral quantization of it, discretize it, so that the derivative becomes a finite difference, has to be matched with covariant derivatives. So I've put in my UN of the x plus 1, parallel transporting x plus 1 back to xn to match them, and then take the difference using this parallel transport, which is where the gauge field enters. And once you do that, you can rewrite the lattice version as this expansion here, and by changing variables, one can move all of the gauge transformation to one side. I'm going to skip this because I'm not going to have really time to do it, but it's in the transparency, so someone wants to look at it. And eventually one comes down to quantizing it. One has a quadratic form that had to be evaluated up here in the lattice version. One has a quadratic form in the end in terms of the x's, which had to be evaluated. Take the lattice spacing back to 0, and you get this action integral, that z is this integral over the remaining variables after diagonalizing this U, this residual gauge transformation. And one re-expresses it in terms of this z is e to the I times U, and one recovers the Mullian-Weil formula. One can then easily derive the equivalent formula for many matrices. And again, as I said, you can do that integral in one case. So that's the context. For d-dimensional D matrices, we can recover our formal variables by putting in an mk for each of them, and T in the Mullian-Weil is then e to the minus mk times beta. And the Mullian-Weil effective action has this this expression SGG. The first term is arising from the double sum when I is equal to j. I've pulled it out. It's independent of theta. And the remaining terms, they look like Vandermon's, but some deformed one with a tk in there. And that's what the expression is. So I'm actually going to skip this because I'm going to run out of time. I just wanted to show you how this one would work if I just had one variable, a simple variable. These type of generating functions are used and this type of counting problem is used when you want to know in particle physics if you've counted all of the operators that are higher dimension operators in the standard model. There are an enormous number of them there. It's a significant problem to be sure that you've got every operator if you wanted it in treating a low energy effective action for the problem. You would like to be able to count it, and you'd like to be able to be sure that you've counted it. And these same techniques are useful in that setting. And they're standard when I've given one reference to that here. And I just wanted to show you how this counting works in the simplest setting, where one takes just a charged single variable. This is essentially a harmonic oscillator with a constraint that it should be invariant under this phase transformation. Then the partition function then is given by that what I've derived earlier, and one can write it down as z as being this quantity, and you see that the invariants are just expanded in terms of t and t star. And that's just another way of looking at it. Okay. One wants to now just try and extract some of the physics from this. I started at 10 past, okay, 10 minutes. The problem has been mapped into one at finite temperature, and we have an effective action for it. And we're interested in a partition function. Expanding the partition function gives us our counting variables, so we can count how many there are asymptotically at large beta. That's going to tell us how the number of invariants grows asymptotically at large n, at large t. For the dimension n grows asymptotically. So if we expand it as beta goes to infinity is the low temperature limit of the system, and expanding we can expand the logarithm here. You can see that the expansion of in terms of t, I shouldn't expand the Vandermonde, but if I expand in the first term, we can re-express it in terms of mod of un to the squared with some variable in here. And when we do this, we can re-express those variables. We can just call them an, And if we just keep n equals 1 term, we get what's called the A1 model, which is closely related to the Gross-Baidie-Witten one plaquette model, which many people will be familiar with. But this one is called the A1 model, and it captures many of the features of what we're interested in. I should have said that since t is much less than 1, that we're going to capture the low temperature phase of the model by just picking the A1 term here, the n equals 1 term. At high temperatures, we're going to get a dimensionally reduced version of it. We are the lowest mode in expanding in this T1, this circle, gives us just the constants in terms of the gauge field A, and we get this single matrix model with a commutator of x times these, and we can then just rescale to pull out the dependence on beta, and we can obtain that the dimension of n, this asymptotic form at large n, grows as n squared d minus 1 log n. And one of the important things is that there's a phase transition between the small temperature and high temperature. And to see that, if I expand the Vandermonde as well, I can regroup that earlier expression as 1 minus a n, and we see that a1 is equal to 1. That term for a1 changes sign, and since the a1 is given by these sum over I equals 1 to d of ti, and an is ti to the d, that same sum, it's positive, and the first one to become negative of those 1 minus an has to be a1, and it occurs at a particular temperature, which is th, which is 1 over log of d, where d is the number of matrices, and this is a Hagedorn phase transition in the system. One can formally just integrate over the UNs in this variable up here, as written, and treat the UNs as approximate continuous variables, and get z equals z infinity, and you see that it's equal to this expression here. This is in fact exact for n equals infinity, taking n goes to infinity, sitting in the low temperature phase. It gives you, this is an exact result, and you see that there's a pole in the expression when n is equal to 1. So that tells us that these coefficients, that something happens, that's where the phase transition is, and that's the Hagedorn transition. We could expand that out. We take the z infinity of t, expanding in t, we get the dimensions. So you can see that the dimensions as n goes to for n equals infinity, they grow as d to the n, which is growing exponentially. And so we have an estimate of what these dn are for small n. But this expression breaks down near the transition. So to estimate these dimensions for dn for large n, we can still use the A1 model, because the transition is occurring at beta is equal to, or at t is equal to 1 over d, and d is more than 2, or even more than less, is 2 or more or greater. So if we we can get a reasonable estimate of what's going on in the, at finite n by focusing on the A1 model. Expanding the A1 model, we can expand it in powers of A1 and just use some group theory to re-express the partition function for the A1 model in terms of as written there. The dn give us the dimensions of the representations of the permutation group, and we can write out what they are exactly here. We have also that 1 over k factorial dr of sk squared is 1 for k less than or equal to n, and that's just an identity. And I've just plotted some of the coefficients here for you in comparing the n equals 5 with n equals 8 in the A1 model. And you see that they cut off rather sharply not at n, where one might expect, but at a larger number. For large n, we can look at the other side of the transition, by going to a continuous variable, the density of the eigenvalues of A, which are our theta I. We can go to a continuous variable and write in terms of the effective action in terms of a density of eigenvalues. So we get SGG in terms of rho, where what I've done is I've really just taken theta n, taken it to be a continuous variable of n, and gone to a density of rho and written it as this one. And this is gives me an effective action. This is for the entire system. It isn't really solvable or hasn't yielded to a solution. But if I do it for the A1 model, one can find what the eigenvalue density is. And the eigenvalue density is given by this expression here. It's a change of variable of a Wigner semicircle if you play with it a little bit and you choose the variable s. But it tells us that in some of the details of the transition, that for A1 less than 1, the partition function is 1, essentially. The log of it is 0. And for A1 greater than 1, this is where the transition occurs. It is given by this expression in terms of that. We can expand it in terms of the temperature. We see the nature of the phase transition, and the transition occurs precisely at E equals 1/4. I've given you some graphs just to show you what the transition looks like. But I want to focus more on the entropy, because we're interested in counting the number of states. And the entropy, we can extract the entropy. We've got the entropy of the counting from low temperature phase from the exact expression, and taking n goes to infinity. We're getting the counting from the high temperature phase from this density, but it's only an approximation because we've used the A1 model. If we use the derivative of the entropy with respect to energy being beta, we can integrate back to get beta of E to get the S by integrating beta with respect to energy. We get that the entropy is given by this expression. And we have the entropy as a function of energy above the transition. So we can compare the two. And the transition occurs exactly at E equals 1/4. At low temperature, we have Z infinity of T and D being this one. I'm just rewriting what we saw earlier. Z infinity of T being this exponentially growing with the energy, but that's only valid be up to 1/4. It's matched at S equal at 1/4, the energy being 1/4. We get the energy being log of D over 4. And at the transition occurs exactly at n² over 4. And what it's telling us is that the transition is one where the trace relations can be ignored. We can treat the system as if it was an infinite matrix system up to n squared over 4, but not above that. And then I'm just summarizing what we found here. The dimension grows exponentially as e to the n squared log d of e below the transition. And above the transition, we get this n squared with some, as written there. And the low term, and we've matched that at e is equal to 1/4. There is no jump in the transition. We're at finite n. This is a finite n system. One can compare it with the small matrix size expansions. And it agrees incredibly well with it, actually. So these are, I can finish at this point. This is rephrasing the main results and leave it to questions. All right? Okay, thanks.
Are there any questions from the audience here? Yes. Yes, go ahead, please.
Just one small mathematical clarification. So this phi of 1 by d, so I thought that the Euler-Torsion function is an arithmetic function, right? So you have to take the natural numbers as the input. What does 1 by d, phi of 1 by d mean here?
It's you don't take the natural numbers as input.
This is the Euler-Torsion function, right?
It is the Euler-Torsion function as a function variable. I introduced it earlier. It's the product. It's the generating. It is the partition function of. It's 1 over the partition function of the one matrix model where the variable t is e to the minus beta m, and well, this is just 1 over 5d. Is that, and it's written as it is product from t. It's phi of t. I think that's what it is.
I see.
So t is a variable there. It doesn't have to be. You can take it to be anything you want to and put it into that function.
I see. So, I mean, the one I was aware of is like all the natural numbers and then the number of numbers co-prime to it, like less than and equal to co-prime to it. So that was the Euler-Torsion function, right? Yeah. Okay.
I presume it's an analytic continuation of the same expression.
I see. Yeah, of course. Yeah, it could be that. Yeah.
Yeah, in the sense that you have zeta functions, which are zeta of 2, zeta 3. It's natural to continue them to any formal variable and to their maximum range of analyticity. But this is what I mean by it.
Okay.
And this, it's really, yeah.
There is a question here.
Just a small comment. I was trying to understand Nahm's equations, and it seems to me that the dimensional reduction you are doing, have you done it for f equal to star f, then the same dimensional reduction, not seems to me, you'll get exactly Nahm's equations. Okay? So, you have the exact theorem that you can go back, that the transition from self-dual equations to Nahm is injective, that is, you can go backwards. Okay? This is a Hitchin result. Okay? So I am wondering whether these techniques will throw light on it. That's question number 1.
Nahm's equations are for a monopole system.
No, you can start with self-dual equations, and if you dimensionally reduce it, you end up, if you go step by step, you can reduce it to from 4 to 3 to 2 to 1.
Yes.
Okay? At say at the one level, you get the monopole equations, and the level 1 you get Nernst equations,
Yes.
and it is inject. That is one way you can go backwards. Okay? That is the most remarkable thing about the matrix model reduction. Okay? That's the only model I know where the reduction can be undone, okay? In a rigorous way. Okay? I think I told you this.
You've told me that. I don't see how it could be true, but amazing things happen. I don't see how it could be true for a quantum system.
It is a quantum.
Yeah. No, but
it is
for
a quantum system.
I don't
know.
Because
This I don't
what
know.
you have done is you have reduced the system on a torus, for instance, is the one that I did it on, and I've completely thrown away all of the Kaluza-Klein modes for that.
We'll come back.
To imagine that I could recover the entire system and all of its quantum field theoretic results, I don't think that's true. That could be true.
It's not a classic quantum field theoretic result.
That's why I'm suspicious that it's. Because I have reduced the quantum field theory to a quantum mechanical system. In fact, if you reduce Yang-Mills in more than 4 dimensions, it's not renormalizable. There's no reason to believe that you can absorb all of the infinities into a change of variable, into change of coupling constant. So, whereas I still get a finite matrix model.
So the thing is, I am not very clear on this issue because in between, the Kalia's index theorem comes in. That is it quantum mechanical result or classical result? I don't. Kalia's index theorem is index theorem in 3 dimensions for the Dirac operator.
Yes.
Yeah. Is that classical quantum? It seems to me.
Well, that's a topological statement. So that topology can be rather captured, and I can imagine recovering topology and having retained the essence of the topology in a deformation retraction down to a much lower dimensional system, that the essence of the topology could be captured there. But
okay, we can talk about one more.
I think we can. Oh yeah,
Sure.
You have another question.
Just a comment. I asked in Dublin also, have you looked at correlation functions and whether they factorize or no in the larger limit?
The factorization of correlation functions, they do factorize.
Do you get a classical system then? So there should be a master field.
There should be a master. Yeah, I remember you asked that, and I haven't. The master system really, I don't think it would capture what I was looking for here still, because
There's no question on that. Okay. Then I think we should proceed. So let's thank Denjoe one more time.
Sure.
And